Yes, so welcome everybody to today's edition of the Pacific Quasiworld seminar. So our first speaker today is Mikhail Hlushchanka from the University of Amsterdam, where I'm actually also visiting right now, and he will talk about the independence polynomial and recursive graphs, the dynamical perspective. So please, Misha.
Yeah, thanks, Mario, and thanks to Zhishank and other organizers of this seminar for the invitation. Yes, so I would like to talk about a portion of my work within this project called CODA, called Complexity in Dynamical Systems, Algebra and Geometry. And the general sort of motto of this project is that we want to understand relations between different complexity measures of dynamical systems, fractal sets, graphs, and groups. And today in my talk, there will be kind of not really much of some quasi stuff, but this is the latest thing that I've been working on, and I decided to sort of advertise a connection between the rational dynamics and statistical physics. So just to give you some preview of what is going on in the moment, so I will give you some outline of the theorem, but first I want to say that today we will be concentrating on the dynamical systems emerging from partition functions, and all of I'm talking about is a joint work with Hans Peters from the same place that I am, from the University of Amsterdam. So the main characters for our story today are, as you could see on the screen, so there is independence polynomial and its zeros. There are like some phase transitions, recursive graphs, and some that maybe you are more familiar with, like rational dynamical systems. So let me just, as I said, give you some preview of what will be happening in this talk. So we will be considering a recursive sequence of graphs. Each graph will have a fixed amount of key labeled vertices, and the next iteration of the graph will be obtained by joining m copies of the previous graph by gluing along the labeled vertices of the previous level. So basically, just to illustrate on some example, so this is a recursive sequence of graphs, and the next iteration is obtained by taking 3 copies of the graph of the previous iteration, glue them together, the previously labeled vertices, and then I introduce new labeled vertices. So in this case, I take 3 copies of the previous graph and introduce 3 new labels. So this is just an outline of the recursive construction of the graph. So what we will do with this, so we will introduce some dynamical system associated with this recursion operator. So it's going to be on a multiply dimensional projective space. This dynamical system will have some natural invariant algebraic subvariety, and by analyzing the dynamics of this algebraic subvariety under some extra conditions on the recursion, we will be able to prove the fact that zeros of the independence polynomial for this sequence of graphs avoid a uniform neighborhood of positive real axis. And the physical meaning of this statement in particular is that the so-called limiting free energy is well defined and real analytic on all of real parameters. In particular, there are no phase transitions. So I will, of course, define all the relevant notions throughout this talk. But for now, let me just introduce sort of the main protagonist of our discussion for today, which is the independence polynomial. So suppose that I have a graph. It could be finite. It also could be an infinite graph. So let's just look at this example. A subset of its vertices is called independent if I do not have any edges between the vertices of my chosen subset. So in particular, these 2 red vertices do form an independent set, but if, let's say, I pick these 2 vertices, they will not form an independent subset. Instead of talking of independent subsets, I could also talk of independent vertex assignments. So basically what I'm doing, I will be assigning zeros or ones to vertices. And I say that this vertex assignment is independent if the vertices that get assigned 1 form an independent subset of the graph. In particular, in this case, again, this whole assignment is independent because the vertices, the two vertices which get assigned 1, they form an independent subset. So now what is independence polynomial? Well, it's defined for a finite graph G. So I look at the generating function basically of the number of the independent sets. So basically I have as a sum of the monomials of this form. So I look at all possible independent subsets in my graph, and I raise lambda to the size of this independent subset. Or put it differently, this is really like the generating function of the number of independent sets in your graph. So like for this concrete example, this is exactly the independent polynomials, as one could easily check. In particular, well, for this particular example, there are like no independent subsets, of course, of size 5, but there exists exactly one, which is given by this, all the vertices, all this kind of leaf vertices. And that's why I have monomial lambda to the power 4. Of course, there are like 4 independent sets of size 3 because, well, I could just pick any 3 vertices out of these leaves and so on. So this is something that you could just easily check. So this is the independence polynomial. And what we're really interested in this talk are the roots, complex roots of this independence polynomial. And the reason why we're interested in this is because of some physical interpretations of the independence polynomial, which I'm gonna talk about next. So the title of the next chapter of the story is Partition Functions and Phase Transitions. So the hardcore or the neighbor exclusion model describes the behavior of particles at the vertices of some possibly infinite graph G. They assume that you forbid the presence of vertices at the presence of particles at the adjacent vertices. So in particular, kind of one of the standard physics models is the distribution of some gas molecules within the dual of this kind of graphene lattice. So kind of the gas models are large enough so that the two gas molecules, they could not occupy the neighboring kind of hexagonal cells. And that's why you're kind of forced to look at this independence polynomial. But let me kind of, so this is just some outline. Let me make some precise definitions in a moment. So a spin configuration on some possibly infinite graph G is just any vertex assignment of 0 and 1s, which we could also call spin to the vertices. So for the time being, let's suppose that the graph G is finite, then each state, sigma, or each vertex assignment will be coming up with some energy, which in general depends on one or maybe more parameters. But having this energy, we could define the weight of some configuration sigma, as is done in thermodynamical formula. So you just take the reciprocal of the exponent of the energy. And then you could look at the corresponding partition function, well, which is the sum of all the weights. And the meaning of this is that, okay, like the probabilities that a given configuration appears is just the normalized weight of your configuration. So you just divide the weight by the total sum of the weights. So this is the probabilities that a given spin configuration appears when chosen randomly. So the hardcore model corresponds to the special situation when the energy is described basically by the following formula. So here, the corresponding Hamiltonian depends, basically, it has kind of two separate quantities. One corresponds to the interaction between the vertices, between the adjacent vertices, and the other one, the second sum appears just from the vertex self-potential. So we define the vertex self-potential to be this, where S is just the value of your assignment. So it's either basically, so this guy is either minus log lambda if sigma of V is 0, sorry, if sigma of V is 1, or it's just 0 if sigma of V is equal to 0. And then the interaction potential between the vertices, okay, it's defined to be infinity if you have chosen two adjacent vertices, and otherwise it's just 0. So basically, this sum up here is plus infinity if the vertex set that gets assigned 1 is not independent. And otherwise, it is 0. So remember that the corresponding energy was e to the power minus h sigma lambda. So basically, the only way for the weight, sorry, the corresponding weight was a reciprocal of the exponent of the energy. So this weight is 0 if you chosen some non-independent vertex set, and otherwise it's just this. So otherwise the weight of a chosen configuration is just given by this monomial from basically from a partition function. And that's why the partition function for the hardcore model is just exactly the independence polynomial. So you sum up over all these monomials. So just to summarize this sort of maybe a bit technical discussion, if we look at the natural hardcore model considered by the physicist, then the corresponding partition function precisely corresponds to the independence polynomial of the underlying graph. So let me just mention also in passing is that, okay, there are like other standard models that people consider, particularly the Ising model, which is also two-spin model. And then, okay, basically this is the formula for the corresponding energy. And then there are also kind of something which is called Q-state Potts model. So it's kind of a generalization of the Ising model. And the corresponding partition function is related to the chromatic polynomial on the graphs, well, if you know what they are. But, all right, what do we want to discuss? In this talk, we want to relate zeros of the independent polynomials to some physics term, which is vaguely bit defined, which is the concept of phase transition. So one way to define a phase transition is by looking at the corresponding Gibbs measures. So like if you have a sequence of finite graphs that approximate some infinite graph G infinities, in particular, you could imagine, let's say that you look at the square lattice and you have some finite portions of the graphs as the corresponding approximations, then what we're interested in is basically at uniqueness or non-uniqueness of the corresponding Gibbs measures. So, okay, let me maybe for now skip the precise definition of what it is. But roughly speaking, I will just show you of what is sort of happening on the picture. So suppose that my configuration, so like my graph that I'm looking on is arising from the square lattice. So we suppose that we put particles in the cells so that only particles in the neighboring cells interact. In particular, remember that we assign positive weight only to those configurations that do not have particles in the adjacent cells. In particular, what does it mean? It means that, okay, like if we look at the sort of chess coloring of our board, so in this case, okay, the Winkler chose colors blue and red, then basically our vertices naturally come with a color either blue or red. So like each chosen independent set correspond to some sort of partition like this into subsets of two different colors. And now, okay, let's imagine that we are picking some random independent set, and remember that the proportion with which we pick this random independent set is given by this quantity where lambda is the parameter. So in particular, if lambda is equal to 1, then basically we just pick a random set independently. So there is no structure appearing. However, what is happening if lambda starts to get large? And again, let me just write this formula again. So this is the formula for the weight. the model starts to prefer those configuration that have as many basically as possible, so like for which the size of the independent set is as large as possible. And you could imagine that, okay, like what is the biggest possible independent set on this z-squared lattice? Well, you either pick all the blue vertices or you pick all the red vertices. So basically, after some critical parameter lambda, the independent sets, they start to get some regular structure. In particular, we see that, okay, like when lambda increases, we basically, when we pick a random set, we basically forced to pick vertices of just one particular color. And this fact basically corresponds to the non-uniqueness of Gibbs measures, because potentially, okay, like you have two different colors that you could pick. You could either pick all the red vertices or all the blue vertices, and this would correspond to basically to this non-uniqueness of the Gibbs measure. So there are like two different measures that respect conditioning on finite portions of the graph. So this is sort of the one way to introduce phase transitions in terms of behavior of the distributions for these limiting models. But for this talk, we will mainly look at a different point of view on phase transitions. Namely, we'll be looking at the analyticity of the pressure functions or limiting free energy per site, which is defined as the normalized limit of the logarithm of the partition function. So we look at the partition function, we take logarithm, and then we normalize by the size of the vertex set. So this function is called, well, the pressure or the limiting free energy. And we say that the model has phase transition of order k if this pressure function has discontinuity of the case order. So if it has discontinuity of the case order derivative for this limiting free energy. So today we'll be understanding phase transitions in terms of the analyticity properties of this pressure function. So the folklore conjecture in this topic from the point of view of physicists is that if you have some regular lattice and if you have a sequence of finite graphs approximating this regular lattice, then there should be unique critical parameter lambda c such that you experience basically phase transition. So you have unique Gibbs measure below this critical parameter, and you have multiple Gibbs measures above this critical parameter. However, I should warn that, okay, this is just a conjecture. In particular, even the monotonicity of this behavior of the Gibbs measures, as far as I understand, is not known in the general case for like regular lattices in RD. But what have been observed by Yang Liso in their celebrated work is that phase transitions are closely related to the zeros of the partition functions. In particular, let me highlight this part. So if zeros of partition functions avoid a complex neighborhood of some parameter lambda naught, then the limiting free energy is real analytic at this parameter. In particular, you do not have a phase transition at this parameter. So for that reason, in the second half of the talk, what we'll be interested in is understanding the locus of zeros of the independence polynomial for some sequences of graphs. Any questions about this? Okay, if not, then let me then move sort of to the main sort of part of this talk, is that since regular lattices are hard, so it's very hard to understand what is happening for the corresponding physical models for them. Instead, what we'll be doing, okay, we'll be looking at recursive graphs. So as we will see later, this in the recursive situation, we'll have natural dynamical system, and this will help us to analyze the phase transitions. But before I sort of go to the precise definition of the recursive graphs that we consider in this talk, let me just sort of mention two known results. So if we look at regular rooted trees, so which you could really kind of obtain recursively by kind of taking, in this case, 3 copies of the previous graph and joining them together by this sort of tripod picture, then it was proven by Weber, Letellier, and Sombra that the hardcore model for this sequence of regular rooted trees has a unique phase transition of infinite order. So the fact that zeros of the corresponding independence polynomials accumulate a unique parameter, at a unique physical parameter, and they actually could tell exactly what is the corresponding physical parameter. So for such recursive sequences of graphs, okay, there exists unique phase transition. So then there is also a series of works by Roland Roeder and his collaborators, in particular with Blech and Lubitsch, who prove that for the Ising model on the so-called diamond hierarchical lattices, again, there is a unique phase transitions. So just, again, to give you some idea of how these recursive graphs are constructed. So you start with an edge, and then you replace this edge by a for cycle, and then you iterate. So again, you replace each edge by the for cycle. And then if you do it one more time, this is the graph that you will get. So like each edge is being replaced by the for cycle. Again, an alternative point of view on this guy, instead of sort of doing this replacement of each edge by the for cycle, instead, we could take 4 copies of the previous graph and glue them together at the vertices and build up a new graph. And this is sort of the procedure that we will be doing in this talk. So now I'm going to define precisely how do we actually build up recursively graphs for the purpose of this talk. So I suppose that I start with some graph G, which has k vertices labeled 1 up to k. I take m copies where m is some fixed parameter of this graph, remembering all the labels. And then for each label L, I consider a partition of the set 1 to m. So basically, in this case, I have the partition that corresponds to 1, 2, 3, and 4, 5. And I think of this partition, so each set of this partition as being a hyper edge in my hypergraph, capital H. So basically, each of these sets tells me that I should join the vertices labeled 1 in the copies 1, 2, and 3. And here I should also join the vertices labeled 1 in copies 4 and 5 when I build the next iteration. So I do this for every possible label. So again, like for label 2, I have a different partition in this case. So this is 1, 4, 2, 3, 5. And for label 3, I just have the trivial partition. So it's just 1, 2, 3, 4, 5. So again, for each label, the corresponding partition tells me which vertices of label 2 in the corresponding copies should be glued together. So this edge tells me that I should glue together the vertices labeled 2 in copies 1 and 4. So this picture, okay, maybe it's not entirely clear what does it mean, but it could be drastically simplified in a moment. Sort of, let me just maybe show it right away. So I had a graph with vertices 1, 2, 3. I take 5 copies of this graph and I glue them together basically in the way that is prescribed by these hyper edges. So this is the new graph that I obtain. And the last thing that I should do is, okay, I have to introduce also new labels. So I have to introduce new labeled vertices. And for this, I have the so-called labeling map where for each possible label from 1 to k, I just choose one of the hyper edges. So this is 1, 2, 3. So I have 3 hyper edges in my graph. And I just say that, well, the vertex that would correspond to this hyper edge will get new label 1. So this is what this is the new picture. So again, let me just maybe show some very concrete examples. So this is exactly sort of this construction of this Sierpinski gasket graphs that I showed you at the very beginning of this talk. So I take 3 copies of my graph and I glue them together at 3 vertices and introduce new labels at the endpoints. So this is just like, so I take these 3 copies of this graph, glue them together as prescribed by this picture, and then I label these vertices. And okay, maybe just let me show you another picture. So this gluing scheme corresponds to or the simplified version corresponds to the dendrites that you get by looking at the Hubbard tree for z squared plus I, and then iteratively taking the pullbacks, the preimages. So basically, if you think of this tripod as being your Hubbard tree for z squared plus I, then these pictures corresponds to the corresponding preimages of the Hubbard tree. And okay, in this case, all of these graphs are dendrites. Okay, so the branching points in this case, they have either degree 2 and 3. And again, you know, like this labeled vertices that basically correspond to the location of the post-critical points for this z squared plus I polynomial. All right, so this is the class of graphs that we work with. So now I have to introduce some special restrictions on the models that we consider. So we say that the recursive scheme or recursion R is not degenerate if when started with a connected graph G naught, all the vertex degrees of the graphs stay uniformly bounded. So in particular, if I look at this z squared plus I things, so the only possible vertex degrees in this case are just 1, 2, and 3, so they stay uniformly bounded. So this guy, the corresponding recursion is not degenerate. However, if I look at this diamond hierarchical lattices, they would be actually degenerate because the vertex degree of the labeled vertices, it blows up, it grows exponentially fast. Because remember, so in this diamond hierarchical lattices, what do? I take 2 copies of the previous graph and I glue them together at the new vertex. So basically this, the labeled vertex would have degree 2 to the power k, where k is the iteration. So here, this is degenerate. And I want to also introduce one more definition. So I say that the vertex, so that I say that the recursion is expanding if for connected starting graph, the distance between vertices having different labels diverges to infinity. So I have my graph from some iteration n, and I look at the distance between labeled vertices in the graph, and this distance should diverge to infinity. In this case, I say that the recursion is expanded. So it may not be entirely clear why z squared plus I, sort of why the original recursion for z squared plus I is expanded, unless sort of you understand that this exactly corresponds to the Hubbard tree and its preimages. But okay, like in the case of this diamond hierarchical lattices, it's clear that the distance between these 2 labeled vertices, again, it grows as 2 to the power n. So this is an expanded one. Any questions about recursion operator and these 2 terms, non-degenerate and expansion? All right, if not, okay, so then what do we have so far? Okay, so we have defined recursive sequence of graphs, and we introduced also these 2 special subclasses that will be important a bit later in the talk. But for now, it's time for a new chapter, which is dynamical system. So basically now, having a recursive sequence of graphs or having a recursion operator, what do we want to do? We want to introduce some natural dynamical system that allow us to compute the corresponding partition functions. And basically the idea is that we want to partition the partition function. So remember that we look at the sequences of graphs with k labeled vertices. So I denote by L of G the set of labeled vertices. So this set will have exactly k vertices. And then for any vertex assignment on this labeled set, L of G, each such assignment I could think of being just some binary k tuple. I could look at the subpartition function which corresponds to those independent vertex assignments that agree with the assignment, with the chosen assignment on L of G. So basically, I sum up only those vertex assignment sigma which get exactly this assignment on the labeled vertices. So clearly, the whole partition function is just the sum of all the things over all possible binary k tuples. So we partition the partition function. So basically, now we have a natural coordinate map from the set of graphs with k labels to 2 to the power k dimensional complex space, where you just take for each chosen k tuple, in particular for the zero tuple, you just look at the value of the corresponding subpartition function at the given complex parameter. So we have a natural coordinate map that I denoted phi lambda. So now the main claim here is that the coordinates for the next iteration of my recursion could be expressed as homogeneous polynomials in terms of the coordinates of the previous iteration. So again, let me just sort of describe this on some example. So this is just the gluing scheme of my Sierpinski recursion. I take 3 copies of the graph and I glue them at these 3 vertices and I assign new labels like this. So just to simplify the notation, let's denote this subpartition function by this guy and the subpartition function of the next iteration by prime. Then what do I have? I have that the x1, x2, x3 prime, where x1, x2, x3 are labels, are the is the assignment to my labeled vertices of the new generation. So this can be computed using the following formula. So basically, if you have any independent set in this bigger graph, you could split it up as an independent set in each of the copies. So the thing that you have to keep in mind is that if you chose vertex, one of these vertices independent set, then you will have to compensate by this factor because this vertex was counted twice, basically, if it was chosen. So basically, just by doing simple combinatorics, we have that the new coordinate is given by the homogeneous polynomial of degree 3, where 3 correspond to the number of copies that are glued together. Well, okay, I have this some compensation to also keep in mind, but okay, we keep the parameter lambda fixed for now. So this is just a homogeneous polynomial of degree 3. So what does it mean? It means that, okay, I have a natural semi-conjugacy. So from my recursion operator R upstairs to this map F lambda, where each coordinate map is a homogeneous polynomial. So what we can do now, of course, we could just projectivize the corresponding coordinates. So the degree, so we have one coordinate last after this normalization. And what is now phi lambda hat? Well, it's just a rational map in this projective space, in this multidimensional projective space. And what we were interested in, well, we were interested in the zeros of the partition functions, right? So we had a graph up here. We have the corresponding partition function. But remember that the corresponding partition function is just the sum of these coordinates. So, but of course, if we're just interested in whether the sum of coordinates is 0 or not, we could also just look at the sum of the coordinates of the corresponding projectivized versions. So basically the sum of the coordinates is 0 if and only if the projectivized guys also sum up to 0. So instead of basically looking at independence polynomial, what we want to understand, well, we want to understand the iteration basically of this dynamical system phi lambda hat, and we want to understand when the sum of coordinates is 0. So this is what we are after in this discussion. So we transferred the question about roots of the dependence polynomial to understanding this dynamical system and the vanishing of the sum of the coordinates of the iterates with respect to this dynamical system. And this is, so understanding the latter is something that I'm gonna talk about in the remaining part of the talk. So chapter 3.
So Misha, sorry to interrupt. Before you go to the next chapter, can you go back again? I mean, I'm a little confused by the homogeneity here.
Yes.
So can you explain this again? So why do you get homogeneous polynomials in what are the variables actually?
So the variables are given by these values of the subpartition function.
But lambda is fixed, right?
Yeah, so for now I keep always lambda fixed for now. So lambda is fixed. So then the new coordinates, so the new coordinates associated with my, the next iterations, they're given by the products, by the sum of the products of degree, of three multiples in this case.
Right, and this lambda factor, I mean, it's just a constant.
I mean, here, yes, since we keep lambda fixed for now, and this is just a constant. So that's why, here, my dynamical system depends on lambda.
Yeah, I see. Yeah, okay.
So I have a rational dynamical system which depends on my given parameter lambda.
Yeah.
Okay, so now the next chapter is our new main character, which is invariant variety. So what I want to do, I want to consider the variety in my projective space defined by the following equations. So here, remember that my coordinates naturally corresponds to k tuples. So I want to define the system of equations like this. So I look at all k tuples x and y such that their sum, coordinate y sum, is still a binary k tuple. And then I consider the corresponding equation like this. So the product of x tuple times the product of the y tuple equals to the product of x plus y tuple times the 0 tuple. So basically, this is one equation that I get, but now I look at all such equations for all possible binary tuples x, y, such that their sum is still a binary k tuple. So in particular, okay, maybe just to give some intuition, okay, if I only have if k is 2, then basically I only have just one equation of this sort. But if k is 3, okay, you have equation, let's say, like this, or you also have equation maybe like this, and so on. So in this case, there are other equations. So I consider an algebraic variety defined by this collection of equations. And the claim is that this variety will be invariant under the dynamics. So maybe, to just give you some intuition, I will in a bit interpret this in terms of probabilities. But for now, let me just make some remarks that this variety depends only on the number of labels. In particular, it's independent of the recursion itself. So it's independent of the way I glue things up. It depends only on the number of labels. And now, okay, as I said, so this can be proven directly using just the formula for f lambda, but it could be also proven alternatively using the probabilistic interpretation of this variety. And I will tell you in a bit what it is. So basically, if I have any vertex assignment tau on my labeled vertices, I could look basically at the normalized probability. So I looked at those. So the probability of tau is the sum I sum up over all independent set sigma which agree with tau on the labeled set. So basically what is PGT is the probability that if I choose randomly an independent vertex assignment, then the vertices in the set L get exactly the assignment tau. So this is just what is PG tau. And then the crucial point is that this variety may be defined in terms of this probabilities just by this easy formula. So if I have any two assignments, tau and tau prime on disjoint subsets, then the probability of, well, okay, so when I say here intersection of the assignments, I mean that, like I take basically the union actually of the assignments. So I look at the assignments given by tau on one subset, and I look at the assignments given by tau prime on the other subset. Then this probability is given by the product of the two probabilities. Or put it differently, there is no correlation between the labeled vertices. So the assignments on different labeled vertices are independent of each other. And as you could now imagine that, okay, like basically the interpretation of this invariance is that you suppose that there was no correlation between the labeled vertices in the nth generation. You could also deduce from here that there is no correlation between the labeled vertices in the n plus first generation. So basically you could make it precise and prove this invariance of this chosen of this variety in this kind of probabilistic way. So again, what did we discuss at this moment? So we have a variety in our projective space, and it's invariant by the dynamics that we study. So the next thing that I want to tell you is what's happening actually on the invariant manifold, and afterwards we'll let us to discuss what happens near the invariant manifold. So on the invariant variety, if we have this extra condition that the recursion is non-degenerate, so remember, non-degenerate means that the vertex degrees do not blow up under iteration, then the manifold is eventually periodic. So after passing to some iterate, basically, there exists some sub-manifold to which we collapse. So if R is non-degenerate, then basically the dynamics on the manifold is, okay, dynamically not interesting. It's just eventually fixed up to passing to an iterate. And near the invariant variety, we actually transversally superattracting. So basically, if we start nearby, then we will converge to the invariant manifold. So basically, if we start somewhere where we had correlation of epsilon orders of, so like if the difference between the conditional probability of t condition to t prime and the probability of tau was less than epsilon, then after applying the recursion, the difference now would be of order epsilon squared. So we suppose that sort of all these differences are of order epsilon, then on the next iterate, the difference would be of order epsilon squared. So we are converging exponentially fast to the invariant manifold if we start nearby. So this is something for you to remember. On the invariant manifold, okay, we are eventually periodic if we are non-degenerate. And if the recursion is expanding, then we eventually, so if you start close by the invariant manifold, we actually converged it. Okay, maybe let me, in the view of the time, let me maybe skip this. So now, one extra ingredient that I need is to tell you about what will happen if we start somewhere from the physical parameter. So remember that for now, I didn't actually let my parameter vary, but suppose now that I pick some parameter lambda on the positive real axis, which corresponds to basically physical values. So then the statement is that if the recursion is both non-degenerate and expanding, then the sequence of iterates eventually converges towards the invariant manifold. So put it differently, the correlation between the labeled vertices decreases, and actually exponentially fast in this case. So like the fact that this difference converges means that we are getting close by the invariant manifold. So if lambda is the positive real number, if we start our iteration from the coordinate that correspond to the subpartition function of some graph G naught, so we iterate the function and we converge to the invariant manifold. So this theorem tells us what happens with the physical parameters. And now what we can do, we can put all of those things that I just told you about together and actually get data about absence of zeros. So the main theorem is that, okay, like under the two restrictions of the graph recursions, non-degeneracy and expansion, the zeros of the independence polynomial, they avoid a uniform neighborhood of R plus. So this is the theorem. And here is a brief outline of the proof. So we pick some real parameter, positive real parameter lambda naught. We look at the corresponding values of the subpartition function. So this is phi lambda naught of G naught, where G naught is a starting graph. We projectivize them up. We have a point in the projective space. By the previous result, we know that when we iterate our function, we will converge to the invariant manifold. And because actually the invariant manifold is collapsing to the fixed submanifold up to passing to an iterate, we actually converge to this sort of fixed submanifold up to passing to an iterate. But now the point is that because we started from the physical parameters, this value at the limited parameter C naught could not have some of the coordinate equal to 0. Because remember, I mean, we are substituting lambda naught, so all the subpartition functions, they have strictly positive values. So they sum up always to something positive. So this limiting guy also will be summing up to something positive. And now we could start to do the perturbation. So we know that, okay, basically now we could choose a neighborhood here, but the sum of the coordinate is still not 0. And we know that if we start in this neighborhood, we will basically converge to our submanifold here. In particular, our sum of the coordinate is still not 0. So we can pull this neighborhood back and get a neighborhood of our starting point, for which, if we iterated this up here, sum of coordinate is never 0. And then, okay, like we pull this neighborhood back, and we have a neighborhood of our physical parameter lambda naught, where the sum of for which the sum of coordinates never vanishes under the iteration. So basically, this is the idea. So like just using the knowledge about the physical parameter, we could also do some perturbation of the physical parameter and deduce that in this neighborhood, we avoid zeros for all the sequences. And okay, using the Li-Yang theory of zeros, okay, it means that the limiting free energy is real analytic. In particular, there are no phase transitions for the corresponding models. So this was basically the main result. And okay, in just the remaining time, let me just maybe skip this and just tell you some questions that are still open and are very interesting to study. So what can you see about some other models, in particular the Ising model? So basically this sort of procedure that I described. So if we have the situation when the model kind of has some local behavior, like the Ising model or the Potts model, then we could still do this recursive procedure. So the corresponding partition functions would be still described by some dynamical systems. So in particular, we could set up this iteration and still talk about zeros, about vanishing of these coordinate maps for these partition functions. We could also, instead of identifying labeled vertices in the copies directly by gluing them together, we could also instead glue the corresponding copies by sort of using some subgraph instead. So I have, in this case, 3 copies, but instead of gluing them at vertex, I glue them by this tripod. And actually, this significantly influences the dynamical system. So we still have invariant manifold M, so this still remains true. But what is happening is that the dynamics on this invariant manifold is not longer eventually periodic. And this is basically the reason why for this sequence of regular rooted trees, there exists actually a phase transition. So the dynamics on this invariant manifold, so there is some kind of parabolic fixed point involved, and the phase transition arises from a careful analysis what's happening at this parabolic fixed point. So in particular, this is just basically the picture for this sequence of graphs. So this is just some kind of numerical computations of the roots of this independence polynomial, and the thing on the right is the bifurcation locus for the family z goes to 1 plus lambda over z to the power d. Well, in this case, d is equal to 3. So it's z to the 3, where lambda is the physical parameter. So this is the bifurcation locus. At the centers of the hyperbolic components, they precisely correspond to the roots of the independence polynomial. And as you could see, so basically this is the point where the phase transition occurs. And you could see that the hyperbolic components, and in particular the centers, accumulate at this physical parameter. And that is sort of kind of the reason why for this regular rooted trees, you have a unique phase transition at this point. So there is a close relation to the bifurcations of some natural dynamical systems. And just a final question before I finish, we could also ask, okay, do zeros equidistribute? And if yes, okay, what is the support of this measure? In particular, again, like in these situations, zero do equidistribute, and they equidistribute the corresponding bifurcation measure. But okay, is there some sort of general statement about equidistributions of zeros? So, okay, that's something that is unclear at the moment, but it would be very interesting to study. So that's it. Thank you for your attention.
Yeah, thanks a lot, Misha. So let's thank the speaker. And let me start the discussion. So are there any comments or questions? So let me ask you, so what is actually, I mean, you sort of explained it, but maybe I didn't fully follow. What is a good way to think about these phase transitions, right? I mean, you defined them in terms of the zero of the partition function.
Yes.
But is there some kind of an intuitive way of maybe get some idea why you want to call this actually a phase transition?
Yeah, so I mean, the intuitive phase really kind of arising from this sort of from this probabilistical interpretation of phase transition as non-uniqueness of Gibbs measures. So basically, okay, let me maybe just give you a little bit of more details. So suppose that, like I have some infinite graph G infinity, and you have, let's say, some finite approximation Gn of this graph, okay? What you can do, you could look at assignment of spins outside Gn. So you look at some assignment sigma on the vertices of G infinity without Gn. And then what you want to do, so basically we're looking at probability distributions on the spin assignments that satisfy the following condition. The probability of an assignment tau condition to sigma should be the same as the probability sort of when I restrict to this finite portion. So this is okay. This is specified, like by this normalized partition functions. But basically, the idea is that okay, like sort of the things that I see on finite scales should be exactly correspond to the conditioning. Should be so conditioning to this finite scale should precisely correspond to what you get from the explicit formula for finite graphs. So now where does sort of this phase transition come from? Well, okay, if I look at this square lattice, as I was saying, okay, like for large parameters lambda, we tend to prefer those independent sets with as many vertices as possible. And in this case, there are basically two different kind of largest independent sets. You either pick all the blue vertices or all the red vertices. And this corresponds actually to two different Gibbs measures. So one of them would be really kind of preferring black vertices, and the other one would be, well, blue vertices, and the other one would be preferring red vertices. So basically, a phase transition in these terms is basically the bifurcation of this Gibbs measure.
I see.
And then, okay, like this sort of Lee-Yang theory tells you that if the limiting free energy, so if for the corresponding partition functions, zeros avoid a complex neighborhood of your parameter lambda naught, then this limiting free energy is analytic, and also you have a unique Gibbs measure.
Yeah, I see. Okay. Are there other comments or questions? Well, maybe I have one more question. I mean, this whole idea, right, of using some kind of a dynamical system based on some kind of self-similar procedure is very, very general, right? So instead of working with partition functions, I mean, there should be other similar problems for, I don't know, self-similar fractals or graphs where this can be applied, actually. Do you have any thoughts in this direction?
Well, I mean, there are like different things, okay, that people study. So there is this one branch of the research which deals, as you said, with partition functions. Then there is a sort of another branch of research, let's say, that that is interested, let's say, in spectra of the Laplacian operators. And again, I mean, like if you have some regular structure like a lattice, okay, it's very hard to understand what's happening with the spectra of the Laplacians. But once you have some natural recursive construction, and better, you have also some sort of local cut points, kind of some kind of finite local cut points behavior, then you could still naturally set up some dynamical system. So I would say that in general, like the two natural frameworks where I saw this sort of ideas appearing are like renormalization sort of operators induced by looking at the partition functions of different physical models or at the Laplacian operators. I mean, of course, you could also kind of try to generalize this, but I mean, like we still sort of don't know that much. I mean, unless, like we can, so you could always write down basically this normalization operator, but understanding the dynamics of this normalization operator, that's a very difficult thing in general.